Space trusses. Well, I hope that you have already heard about these structures. These structures are very common because wherever you go, ranging from a pole to a communication tower, you will see space trusses. And we also use these structures where we need big spans. Like, have you seen the Othane Mall here? Othane Mall?
Yes.
Yeah. So if you go inside, you will see the roof of the whole Othane Mall as a three-dimensional truss. Okay? Because, like this, if you see, the structure is a three-dimensional roofing system in which, again, the load is applied at the panel points here, here, and these are the joints. And if you see that at each joint, the members are going in all three dimensions. Like in a truss, the members are in two dimensions, X and Y. Okay? One truss this way, one truss here, and you connect these two trusses by perpendicular members. But in 3D truss, the members are projecting out of the joints and going in each direction. Well, before the computer technology, it was very hard to solve these structures because, you know, sometimes the behavior becomes much more complex when you connect the roof with the top chord. I don't want to bring into that discussion a composite action. When you connect the top chord with the concrete, then there's a kind of composite action. We are just focusing how to analyze the forces in a three-dimensional roofing system or a truss. If you see at these points, the load is transferred at the joints, and then from these points the load will go to the members this way, and maybe in the horizontal direction. Okay. So these are typical joints. I think you have seen these joints, and the support conditions are much more similar like two-dimensional trusses. It is a pin joint. All truss elements in case of three-dimensional truss are pin joints. If you want to solve them by method of joints and the method of sections. For example, if you see in this case the member is in which direction? Positive X or positive Y? Positive Z, which direction? This member. Minus X. That's
Going this or this, I don't know.
Well, it's up to you. But if you have given such type of axis, it means the positive in this way. Okay? But if you don't have such axis, you can pick any point and you can decide your own axis. It will not change the end result. It will be the same. This is a kind of collar support. I think we have seen such collar supports, or you can say the roller, because it has only one reaction which has the components. It is a typical. This is a typical ball and socket joint. Well, now the stability and determinacy. It's very simple. Like for the two-dimensional truss, you have M plus R minus 2J. Do you remember?
Yes.
Minus 2J. Why 2J? Because the members or the forces were in two-dimensional axes, X and Y. Why here 3J? Because now each joint can move in three dimensions, X, Y and Z. So that's why we have 3J. The rest of the procedure is very similar. If M plus R is less than 3J, it means it is unstable. Or if M plus R minus 3J is negative, it means it is unstable. And if they are equal, it means it is statically determinate. And if it is greater, 3J is greater than this M plus R, then it is statically indeterminate. What is 3J? J is the number of joints, R is the number of reactions, and M is the number of members. Okay, now, well, these are the assumptions for design. And once you assume anything in a design process, you have to apply the same concept during the construction. Keep in your mind. For example, you are assuming a roller support for some structure, for a beam. Then you have to provide the roller support when you will make that beam. Do you understand this point?
Yes.
If you don't do that, what will happen?
Design what?
Your assumptions, because during your design you assume something that okay, these two joints will be fixed. But when you have provided the hinge joint, then it will be different. It will be different. I mean, it will be not correct design. So whatever you are going to assume, you have to provide in the real design or in the real construction the same idea or the same concept to use it. Well, method of joints. It is very hard to solve a three-dimensional truss with the method of joints and with the method of sections. It's very hard. Do you understand why?
We have three type of forces.
First, you have a good judgment in your mind. For example, let me show you some sample problem here, like this. For example, if you have to solve this joint by the method of joints, first you have a good judgment. This axis is
X-axis.
x-axis. It is z.
Yeah.
Sorry, this axis is
Y.
not x-axis.
Y.
This axis is y-axis. See here.
Oh, okay.
And this axis is x-axis. Suppose you have a good judgment, and then at this joint now you have to think which members have x components. Which members have x components?
All of them.
All of them.
All of them.
Yeah, almost all of them. Yeah, you're right. At this
Except-
joint. And how many have y components?
Three. Yeah, three.
All.
No. Only DE is straight. Only D is straight. A, E, B, E, C, C, E.
And then you have to resolve each force, like when you have to apply sigma fx, you have to consider
The reactions as well.
all the forces and the reaction as well. Okay? And then you have to proceed, you have to apply sigma fy, sigma fz, and if you do any mistake, your answer can be wrong, and it can be not correct. So it's very hard. And same is the way, for example, if you have to determine a force in member AE, so and you say that I will cut a section. Do you understand? So then you have to consider some joint. For example, the moment at this joint will be 0, the moment at this joint will be 0. So you have to imagine in your mind, even if you are good in drawing, you have to imagine that, okay, at this joint, if you take moment, which force you can determine? All these forces will become 0. So if you take moment here, again, all 1, 2, 3, these forces will become 0, but you have to consider the moments due to these two forces. If you cut a section like this, so it means now your section is also in a three-dimensional way. It is not a two-dimensional section. It is just like a cutting plate. You are putting a cutting plate like this. You cut and then isolate the whole structure. Do you understand?
Yes.
So it's not that easy job to solve such structures using the method of sections. Well, but if you want to use, if there is simple 3D truss, like in the beginning, this one, you can solve it, maybe. For the method of joints, again, this is a rule that at least you should have one known force and maximum 3 unknown forces. At each joint, if the number of unknowns are greater than 3, you cannot solve it. Yes.
This I have to.
That is for the 2-dimensional trusses. But for 3-dimensional trusses, you should have
3 unknowns.
3, maximum 3 unknowns. Okay. So this is again the number of equations, 3 equations and 3 unknowns. You will apply sigma fx, sigma fy, and fz at each joint, and you will solve it. Method of sections. Now again the method of section. Now before you have the moment only in the plane. Now before the moment was in this plane the moment was 0.
Yeah.
But now because of 3-dimensional axis, for example at joint D, in this problem at joint E, mx will be 0,
Yeah.
my will be 0,
Yes.
and mz will be 0. And you should think now x. So the moment like this, it will be mx. Okay? And the moment, this is your z-axis. So the moment like this, all the forces which will produce
MZ.
this moment, it will be mz. And all the forces which will produce the moment about this axis.
My.
So you have to think which force is creating moment about this axis. Can you tell me how many forces are creating
A, B, and
at joint A? How many forces are producing moment about y-axis?
A only. A only.
Only A, yes. And what about E?
All of them.
Well, if you talk about the axis, yes. Just consider the joint E. Okay, this is not our discussion. Now we have to solve this problem. I will tell you how you can solve a 3D truss by using Cartesian coordinate system. Okay? I really enjoy using that method.
Sorry.
IJK. Do you remember?
Yes.
Yep.
So it's very simple. Let's solve these truss members by using the Cartesian coordinate system. Okay, if you want to solve this truss, from which joint you can start?
B.
Alright.
I will solve your A has less members, so you start with it.
For example, let's start with joint you are saying A. At A joint, how many unknowns?
Three.
And we have one force.
Okay, I'll tell you the procedure. First, we will decide how many members. Okay, where is your 0, 0, 0 point? Which?
C.
C would be the 0, 0
C.
point.
C.
The decimal.
You're saying the C point is
0, 0, 0.
or the
pick up any point.
C.
C. C.
because Z does come from C.
Yes, coming between E and B.
So if you talk about C, okay, you want to take this point as,
0, 0.
That's okay.
so you can select one point which you will consider 0, 0, 0, 0. Or the other way, just take that joint at that 0, 0, 0 location. Do you understand? For example, if you are at joint A, you can consider this point at 0, 0, 0. It will make your things easier. Do you understand?
Yes.
Because if you are solving at joint B, for example, then you have to keep this as a reference. But if you make this joint 0, 0, 0, and you can find out the position vectors, it will be much easier. For example, it's your choice, but you can consider the point A as 0, 0, 0.
Just for the time being.
Because we
solve.
need the position vectors.
Yes. Fine.
Position vectors are independent of the origin. Okay? Like for example, if you consider this point as 0, 0, 0, let's take this point as 0, 0, 0. Joint A. Let's solve joint A. So it means that now this is our origin. So you have how many forces? You know, if force in a 3-dimension is, for example, if you talk about any force, let's talk about FAE. So this force in a 3-dimensional axis is equal to the magnitude
and to R.
into the position vector R AE. This is the magnitude. Magnitude is like what? Like 5 kilonewton, 10 kilonewton, but you don't know where is the direction. The direction is given by this position vector. Okay? So you can also write this position vector this way, and you know, like Rxi plus R by J okay. But this is, if these are the unit vectors, so you have to divide them by the magnitude. Now, how we can find out the position vector FAE? For example, RAE. How you can find out the position vector? The position of joint E, RE, the position of joint E minus position of joint E minus position of A divided by the magnitude and divided by the magnitude. Very simple. For example, what is the position of E if your A is the origin?
X is 2, Y is 2, Z is
So it will be
Z minus
minus 2.
divided. The simple way it will be
So I.
XE minus XA plus YE minus YA plus ZA minus sorry, divided by square root of all these things.
Yeah.
Plus is it difficult to find out the position vector RAE? No, very easy. Now you have the coordinates of joint E and you have the x, y, z coordinates of joint E and you have the x, y, z coordinates of joint A. Just put the values, you will get the position vector RAE. Okay. What are the coordinates of joint E? If A is the reference, what are the coordinates of joint E? No?
2 and x, 2y, minus 2 and z.
Tell me the coordinates, positive and negative. Hold on.
2,
X,
yeah,
positive or negative?
positive.
Okay, Y,
Because with the that is in y.
okay, yeah, positive or negative. Y, what is the Y coordinate?
Y also 2, positive. the Z minus 2.
Yeah, he's right. Yeah.
Why? How can we get y is negative from?
You decided
I mean, you decided the origin as 0, 0, 0.
Okay, the right.
This point is the origin. Don't think about this point. This point is the origin. So, okay, let's put the coordinate. And so x, y, z, you already put them 0. So I can say 2i. This is j and this is k. 2i plus 2j
minus 2k.
divided by
12.
12?
Square root of 12.
Okay. So what about the answers?
0.577. I have
0.577i plus 0.577j
minus
0.577k.
yeah.
Now this is position vector.
Multiply with.
So multiply with FAE, you will get this force.
4.
So how much will be the force? I need space.
2.31
Okay, I
kilonewton for back to the
So FAE will be equal to the magnitude, you can say magnitude is FAE multiplied by 0.577 I plus 0.577 J 77 K. Or you can also say that if you write this FAE or sorry, just multiply this FAE, it will become plus 0.577 FAE
into I have J.
I Is it difficult at this point?
No.
Any one of you who do not understand till this point? There is the most difficult thing in all this solution of joint. Fine? Now let's find out the position vector of AC.
Just minus 2k over 4 over square root of 4 so 2.
What are the coordinates of joint C?
0,
0, 0,
minus 2.
minus 2.
0, 0,
Minus
minus 2. So if you find out the position vector by this equation, what you will get?
We get just minus 0.57
No.
One
over 1k.
No.
One
It will
K.
be just minus k.
minus k.
It will be just 1 because you know the magnitude and the difference of the coordinate will be same in the z direction. So it is 0.
0.
For this case, Rx will be 0,
Not y
0 I
0 j.
plus 0 J. So it will be minus.
Okay.
If you multiply the magnitude, it will be,
Over.
that's all. Okay, if you are getting confused, I just calculate the position vector of R, A, C. Okay, 0 minus 0 plus
0 minus 0.
plus
0 minus minus.
minus 2. Yeah.
K divided by
minus minus.
Minus 2 square.
0 square plus 0 square. So you will get only
Minus 4.
0 pi 0 j and minus k. Okay.
0.56.
So if you multiply FAE, you will FAC. This will be the position vector. Okay. Now, what about the position vector of AB? FAB.
0 to 0. 0 to 0.
Just override.
Just on X.
0 to y.
0
Just
0
y.
I
0 to 0.
Would be just
0 I
plus j.
plus 2j
Plus j.
plus just j
Yeah.
or 2j.
The ending. Yeah.
2j
هذا الار.
بالاخير بعد ما حسبت الجذر قسمت سويت كل شيء بيطلع لك بس بلس 1 j.
It will be just 1, not 2, because the magnitude will be divided. I mean, the coordinate is divided by the square root of square, so it will cancel out as this here. So it will be
j
plus or minus
Plus.
F A B J plus
0
any other force at joint A.
No.
You have
4. We have 4 turning.
4.
What about 4? How much is the x component of this force?
Minus j.
minus
So,
minus
minus 4 kilonewton j.
So P is
minus
0 I minus 4 J plus.
0.
Now you have how many forces? All forces. Any other force at this joint?
No.
No. Add all these, you will get sigma fx. Add all these, you will get sigma. Add all these, you will get sigma fz. Let's solve them. Okay, now sigma fx. So let's apply sigma fx is equal to
0.
sigma fx is equal to 0 means all these forces is equal to
0. So FAE is equal to 0.
so 0.577. If you add all these forces together, it will be sigma fx. It is sigma fy and it is sigma fz. So sigma fx is equal to 0, so fa is equal to
0.
okay. And what about sigma